Okay, Unit 4 quiz. I'm going to put up the answers here, and you can take a look at them, and then I'll go over the short answer ones, and then if there's any last questions, I'll have to do those on Tuesday, I guess. Okay, here are the answers. Maybe pause it and double check. Make sure I make any mistakes, and then we'll have to sort out mistakes that I make grading and partial credit if you were, had like an answer like this, but in different units, like seconds or something. We'll have to do that tomorrow or Tuesday. All right, I'm going to now go over the short answer problems. Okay, first problem number 9 then says a ball is tied to an elastic string, radius of 8 meters, swung in a horizontal circle of 0.8, and then metallic object is tied to a rope 2.75 meters, and it's swung in a horizontal circle and gives us the period, which is one swing or one circle in 2.9 seconds. And it tells us the ratio of centripetal force to the string of the rope is 1 to 3. And then find the mass of the metallic object. If the centripetal force in the string is 0.2. So they're telling us that this is 0.2 up here. So I can say 0.2 over the force of centripetal of the rope is equal to 1 to 3. And I can, cross multiply and find out that the force of centripetal of the rope is 0.6, and that's in newtons. This is talking about force here, so that's another key piece of information. Next, we're going to find the centripetal acceleration for the rope. So this is the rope here, and we're going to use the formula in our formula sheet for that: 4 pi squared r over t squared, since we're given that information. So we have 4 pi squared. Radius is 2.75 and the period is 2.9 squared. That gives us 12.909 about, and that's meters per second squared. Now I'm going to use Newton's second law. Force of centripetal acceleration is equal to the mass times the acceleration centripetal, and we know that that force is 0.6 newtons. We're looking for the mass, and we know the centripetal acceleration is about 12.909. Divide both sides, and you get your answer for mass, which is about 0.04648 kilograms. And I think I wrote that answer as 46.5 grams. So however you want to write the answer. Okay, the next problem gives us the distance between Pluto and the Sun is 39.1 times that between the Sun and the Earth. Calculate the time taken for Pluto to orbit. So we're looking at a relationship between distance and time, and if you remember, that's Kepler's third law. We've got a ratio here for average distance between, I'll call A the Earth and B Pluto, and then we've got a ratio here for period. Now, it told us that the distance for Pluto is equal to 39.1 times the distance the Earth is from the Sun. So that's that relationship right there. I'm going to plug that in right here. Instead of r sub b, I'll make that 39.1 times r sub a. Now the r sub a's cancel, so I just have 1 over 39.1 on this part of the ratio. And then we want to calculate the time taken by Pluto to orbit the Sun in Earth days. Well, we know then that the period of the Earth to orbit the Sun is 365 days. So we're going to plug that in there and just solve. So I would take the square root of both sides. That cancels. And now we just want to solve this. So I'd probably actually flip both sides. Over 365 equals 39.1 to the, I'm sorry, actually, I can't do that. I'd have to make it 1 over 39.1. Now, obviously, you could just get this as a decimal, but if I'm going to flip this, it was over 1. I've got to put this in the denominator of the fraction now. So 1 over that. And then multiply both sides by 365. So this should give us our answer for the time it takes for Pluto to orbit the Sun in Earth days, because our units were days here. And that gives us 89,239.68 days. Okay, the next problem, we want to find the orbital velocity of Jupiter. So we've got an equation for velocity of a planet orbiting the sun. We obviously want to use that. G times the mass of the sun. Over the average distance between Jupiter and the sun. And we're given all those values. G is 6.67 times 10 to the negative 11 times the mass of the sun they gave us is 2 times 10 to the 30 divided by the average distance of 7.78 times 10 to the 11th. So if you do this in your calculator, you should get the answer of about 13,000 meters per second. Okay, the next problem says the Earth is going to shrink in size and shape, and the mass are to remain the same, but the radius decreases to 0.21 times its original value. And the acceleration due to gravity on its surface. The acceleration due to gravity, we have a formula for that. We call that gravitational field strength, but I showed you where this came from by just taking F equals ma and setting it equal to Newton's universal law of gravity, and I showed you that the m's cancel, and you just get this formula. So we're going to use this to find the new acceleration due to gravity. So g is going to stay the same, mass stays the same. The new radius now is 0.21 times the old one. So I can just rearrange this by pulling out the 0.21, do 0.21 squared, and that gives you 0.0441. And I'll put the r squared here. And so I'll just write this kind of separate here. And this right here is my original value, which we know is 9.8. So this is 9.8. So I need to take 9.8 and multiply by 1 over 0.0441, or take 9.8 and divide by 0.0441, which gives us our answer for our new gravity, which should be 222.2 repeating, and that's meters per second squared. All right, then the last problem gives us a satellite orbits Jupiter. Here's Jupiter, we've got a satellite up here. And then it gives us some information. It gives us the radius here, and it gives us this height. It says this height is 6.4 times 10 to the third kilometers, but we want to use meters, so let's use 10 to the sixth. And I know I'm going to have to get some partial credit, because some people probably the only mistake they made is left it as 10 to the third, in which case, obviously I'll give you -1, I'll do that when I get back. The radius of Jupiter here is 7.15 times 10 to the 7th meters, and we have the mass of Jupiter, which is 1.9 times 10 to the 27 kilograms. So we're going to use our formula for period of, on our formula sheet it's called period of a planet orbiting the sun, but it works for anything orbiting anything else. We just have to make sure we use the right r, which in this case is these two added together. And we have to make sure we use the right mass, which in our case is not the mass of the sun, but the mass of Jupiter, since that's what's causing the gravitational field and the satellite to orbit. So if you add these two together, you get about 7.79 times 10 to the 7th. I'm going to have to cube that. Times g, which is 6.67 times 10 to the negative 11, times the mass of Jupiter, which is 1.9 times 10 to the 27. So just make sure you plug this in right. Use parentheses appropriately. I'd usually start with this number, cube it, and then divide by this in parentheses. Then take the square root of that answer and multiply that answer by 2 pi. But if you do that, you should get about 12,135.2 seconds, which is what our period is going to be in. Now, if you give this answer in something else like days or minutes or whatever, hours, I'll have to give you partial credit for that, or I'll give you credit for that as well. So we'll look at that when we get back, but hopefully this helps in the meantime, get you guys ready for your test.